Now this is a topic that's very closely linked to the rest of algebra but confuses people with the signs. Let's go. So let's start off with those signs. Inequalities means not equalities, not equal signs. So we have four different signs that we can consider. We've got a greater than, a less than, greater than or equal to, and a less than or equal to. I always found it useful to just think that whatever the smaller end is, this is the side that is got the smaller number on it. So it would be true to say that 9 is greater than 7 because 7 is on the smaller number of the equality. If we wanted to put it in other way around, we'd have to write them something like this. However, you don't just have to look at a sign and say what it is. We have to do things with it. So the very basic level is we can be given inequalities like these, and we can ask to draw them out and to talk about the integers they could represent. Another definition that's worth saying in here, integers, that means whole numbers, and they really love that word in inequality questions in GCSE. So how could we interpret these? Well, the first one, that is x is greater than 7. What would that look like as a diagram? Well, we draw a number line and we mark that number 7 on that number line, and we say, well, which side is greater? Do we want the left or the right? We want the right-hand side. The right-hand side contains numbers like 8 and 9 and 10, which are bigger than 7. We draw a circle to say 7's where we're starting, and that's all you have to do. Okay? What integers does that represent? Which whole numbers does this represent? Well, it represents everything which is bigger than 7. So starting with 8, all the way to 9, to 10, etc., and so on forever. What about the second one? X is less than or equal to 10. Number line, 10, circle on 10, and then we want to be on the left-hand side. You will notice that whichever direction this arrow is pointing is the same as the arrow on our number line. That's well worth remembering as a sort of shortcut. However, there's one extra thing we've got to do on this diagram, which is that we can be equal to 10. And the way we indicate this on our diagram is we shade that circle in. Shading that circle in means that we can be equal to something. Not shading it in, as we did over here, means we are not equal to 7. We are greater than 7 in that first example. What are the integers that would work here? Well, everything that's less than 10, but also 10. So 6, 7, 8, 9, 10. We're not going to write down every number in existence, so we'll do a dot, dot, dot on the left-hand side there. What about this? Well, this is a nested inequality, we call it, where it's sort of got two numbers it's in between. So we would mark on again both of the numbers that are in the question, the 3 and the 9. We would draw a circle on both of those numbers, and we would join that up because this just means in between. Is there anything we're missing here? Well, we have a less than or equal to symbol on 9, so that means we have to shade in the circle on 9. Which integers does this involve? Well, it involves everything between 3 and 9, but not 3, because we would definitely have a less than symbol there. So we would go all the way from 4 up to 9, and we would include 9 because we've got the equal to symbol there. Very last one, draw our number line, -5 is the key number, circle, arrow to the right because arrow's going to the right, and shade it in because we can be equal to -5. What are our integers here? Well, -5, and what are the numbers that are bigger than that? -4, -3, -2, etc. Don't get confused with your signs there. So, key point there, smaller numbers on the smaller end of the sign. I've also heard people always say the crocodile eats the bigger number, and I'm willing to accept that, but I don't like that as an actual way of doing it. But if it works for you, it works for you. One useful trick with inequalities is that if you have your number written on the right-hand side and you find that sort of difficult to interpret, because if you're looking at this one, you might be thinking 7 is greater than b, what does that mean? You can flip the order around if you also flip the sign. So this 7 is greater than b is the same as saying, so flip the order around, flip the sign around, b is less than 7. This second one here, flip the order around, flip the sign around, is the same as saying k is greater than or equal to 18. And this last one here, so flip the order around, 3 and 7 and x, and then change the signs. We actually need to put the greater than or equal to over here, and we need to put that over there. So it'll be 3 less than or equal to x less than 7. So if you find it easier to work with the algebra at the start, which a lot of people do, that's a useful way to do your rearranging. What would the diagram and the integers look like? Well, we've kind of done this already, but let's do it quickly. We'd have a 7. We'd have a arrow going to the left, because on our rewritten one, it goes to the left. And we want the numbers that are less than 7, not filled in circle. 18, arrow going to the right, filled in circle. 3, 7, circle on each. In between those two, fill in just the 3. And lastly, what integers do these represent? Well, less than 7 would be, I don't know, all the way from 3 up to 6, but not including 7. The second one would be 18, 19, 20, etc. And this last one, would it include 3? Yeah, because we've got a less than or equal to symbol on it. Would it include 7? No, because we don't. So yeah, useful little rewriting trick that I thought was worth pointing out before we went any further. Now, the majority of what you'll have to do with inequalities on GCSE is solve them. And fortunately, this is incredibly similar to, although not exactly the same as, solving linear equations. There's a previous video, you can go and look on that if you've forgotten what that's about. But it boils down to doing the same to both sides of the equation. So I've got my equations on the left side here. I've got my inequalities on the right-hand side here. And we're just going to look quite how similar these are. So for our first one, 7x plus 15 equals 64. That's an equation. We would subtract the 15 from both sides, which would give us 7x equals 49. And then we would divide by 7. And we'd pat ourselves on the back that we've worked out that x equals 7. For an inequality, we would subtract 15 from both sides. So that would give us 7x is greater than or equal to 49. So the only thing that's different is obviously the sign. And then we would divide by 7. And we get ourselves to x is greater than or equal to 7. Job's done. If you wanted to draw that, you could. Number line 7, filled in circle, going to the right. That's all I mean by quite how similar they are. What about this second one here? We've got x on both sides this time, so we're going to have to subtract 3x from both sides, and we're also going to have to add 7 to both sides. So if we do that, we're going to end up with 3x equals 36, and then we're going to have to divide by 3, and we're going to end up with x equals 12. Cool. What's different if we do it as an inequality? Practically nothing. We are going to subtract 3x from both sides. We're going to add 7 to both sides, and we're going to end up with 3x is less than or equal to 36. What we're going to do then, we're going to divide by 3. We're going to end up with x is less than or equal to 12, which we could again draw if we wanted to. So what's different? Well, just the sign is different. If it had a greater than or equal to symbol at the start, your answer should have that as well. It's the number one place people go wrong on that. So we said it's almost the same as linear equations. There is one important difference, and that's this phrase here. If you multiply or divide both sides by a negative number, flip the signs. And the fact that it's a negative number is the important thing. So I'm going to show you how that works in practice, and then we're just going to have a look as why that might be the case. So starting off here with 5 minus 3x is less than 17. First thing we're going to do is take away 5 from both sides. And if we do that, we end up with minus 3x is less than 12. And then we're going to divide by minus 3. And we're going to end up with x. We're going to end up with minus 4. And then we're going to flip the sign. It's no longer a less than, it is now a greater than. Okay? Now, why might this be the case? Well, let's think about a different way we could have done that same question. Instead of taking away the 5, we could have added 3x to both sides. So that would have given us 5 is less than 17 plus 3x. Then we could have subtracted 17 from both sides. We could end up with minus 12 is less than 3x, and then we could have divided by 3. And we could have ended up with minus 4 is less than x, or using our little flip the order, flip the sign thing, x is greater than minus 4. If we want this to be consistent, essentially we're doing those first two steps in one go. When we're dividing by a negative number, we're changing the order of it, and then that's requiring us to flip the sign. Let's see how that works with the other things. So we've got here minus 7 greater than or equal to a half lots of 3 minus x. What would you do in this situation? I think the first thing, you might be tempted to expand the brackets. Let's actually do it that way just to see how it goes. So if we expand these brackets first, we'll end up with minus 7 greater than or equal to 1.5, I guess, minus a half of x. And then let's take away 1.5 from each side, and that would give us minus 8.5 is greater than or equal to minus a half x. And then how do you get rid of something like minus a half? You times by minus 2. So that would get us all the way up to 17 on this side. It would get us all the way up to x on the other, but flip the sign. So we'd end up with 17 less than or equal to x. And if you want to then change it round, flip the sign, we'd have x greater than or equal to 17. Is there another way we could have shown the same thing? Yep. We could again have just expanded the brackets to start with. So we'll get to the same point. But then we could have added a half x to both sides instead. So if we do that, we'd end up with a half x minus 7 is greater than or equal to 1.5. We could have added 7 to both sides, and that would give us a half of x is greater than 8.5. And then we could have times by 2 and ended up with x is greater than or equal to 17. Same answer, and again, we want this to be consistent. About the last one, well, okay, one way we could do this is we could take away 5x from both sides and take away 9 from both sides, and that would end up with us having minus 8x is less than or equal to minus 32. Then we could have divided by minus 8. That would give us x and 4, and flip the sign because we used a negative division. However, that isn't the only way we could do this. Another way we could do it is obviously add 3x to both sides and add 23 to both sides, and that would end up with us getting 32 is less than or equal to 8x, divide by 4, and we'd end up with 4 is less than or equal to x, and then we could obviously do the same thing, change the order, flip the sign, and we get the same answer. Cool. So just bear in mind that that is the thing you've got to watch out for. Now, it's not just single inequalities we can be asked to solve. We can be asked to solve nested inequalities as well. And when we say do the same to both sides, that's still true, except now there's like 3 sides. So do the same to all 3 sides. And again, if you times or divide by a negative number, flip the sign. We're going to have a look at 4 little examples here. First one's fairly straightforward. We've got a plus 8 in the middle, so we're going to get rid of 8 from everything, and we're going to end up with minus 3 is less than x is less than or equal to 9. That's it. What about for the second one? Well, the second one is minus 2x, so we'd want to divide this all by minus 2, and because we're dividing by a negative, that's going to flip the signs around. So this is going to become a less than equal to, and this is going to become a greater than. That would go down to minus 7, x, and 3. So we'd end up with x is between minus 7 and 3, obviously not including 3. What about for our third one here? Well, this is a 2-step. First thing we're going to have to do is add 5 to everything. So we'd end up with minus 15 less than 3x less than equal to 24. And then we'd have to divide by 3. So minus 5 less than x less than 8. We're in between minus 5 and 8. Didn't have to flip any signs there because I didn't divide by a negative. And then what about this last one? First thing I'm going to do is times everything by 4. So we'll have 12 is less than 3x minus 7 is less than or equal to 28. And then it's a normal two-stepper, so we're going to add 7. So that's 19 less than 3x less than 35. And then our last thing is going to be to divide by 3. And you can have fractions, that's absolutely fine. So 19 over 3 is less than x is less than or equal to 35 over 3. You could put it as decimals if you want, 6.3 and 11.6, but I think fractions are a little bit more accurate. So yeah, if you've got a nested inequality, no problems at all, just do the same to all 3 sides. So the last thing you could be asked to do is to give the smallest or largest integer solution to your inequality. And there's basically just 2 steps here, which is that we need to solve the thing and then work out what the integers that fit into it are. Remember from before, integers means whole numbers. So another way of reading these top 2 questions is we want to find the smallest whole number that works for this inequality. So let's solve it first. So we're going to take away 5 from both sides, and then we are going to divide by 3. So that's going to give us 3x is less than or equal to 11, and we're going to put it in decimals because it will make it a little bit easier to see. That is 3.66 ... or 3 2/3. Now, what's the smallest integer solution where x is bigger than 3.66? Well, here's our number line. Here's 3.66. We want to be bigger than it. The first whole number we would come to would be the number 4. So our answer in this case would just be 4. What about for the second one? Well, first thing we want to do is we want to add 2 to both sides, and that would give us minus 7x is less than 21. Then we want to divide by minus 7, and remember, if you're dividing by a negative, that's going to flip the sign, so we're going to go to x is greater than minus 3. And we want the smallest integer solution where that's true. So let's draw our number line, let's draw our minus 3, and we are going to the right. Don't fill in the circle because it is a greater than symbol. What's the first integer we come to? It would be minus 2. Remember, we don't count minus 3 because we are greater than minus 3, or are not greater than or equal to it. So our final answer there would be minus 2. Okay, let's move on, look at some larger integer solutions. First thing I would do here is expand my brackets, and then we are going to add 20 to both sides. That's going to give us 4x is less than or equal to 31, and then we're going to divide by 4, and that's going to give us x is less than or equal to 7.75 or something like that. Again, draw our number line, circle, filled in circle at 7.75, left side of it because the arrow's to the left, and then we want the largest integer solution, so the largest number we could have here would be 7, because that's the first number on that side of our circle. So our final answer there would be 7. What about for this second one? Well, the first thing we do is take away 3 from both sides, and that would give us minus 5x is less than or equal to 25. Then we would divide by minus 5, and remember, if you divide by a negative, you flip the sign. So we'd have x is less than or equal to minus 5, draw a number line, circle minus 5, going off to the left, and we can be equal to minus 5, so that is our largest integer solution. We're not going to need to go down to minus 6. We might have this question though, where it says all possible integer solutions. Now what would we do in that case? Well, solve it just the same as what we've been doing, which is to try and make x on its own. So we're going to divide everything by 2, and that will give us minus 1 less than x less than or equal to 4, and then draw it out. What does that look like? Well, it goes from minus 1 up to 4. We've got circles on both of those. It's in between those two. We shade in the 4 circle because it's less than or equal to it. And so we basically got all the integers in between those two. So we can have 0, 1, 2, 3, and we can have 4 as well. Why can't we have -1? Because less than, not less than or equal to. So that's our final answer. Okay. Now another way they can ask this same sort of question is to ask you to combine your separate inequalities together. So we're just going to run through one example of how they could ask it in this way instead. So the question here is find the range of values of h that satisfies both these inequalities. So we're going to do the same thing as before. We are going to solve both of those inequalities first. So that would give us 3h greater than or equal to 27 divide by 3. It's going to give us h is greater than or equal to 9. We're not going to draw them until we've got both of them though. The second one, expand the bracket maybe. 4h minus 12 less than 43. Add 12 to both sides. This will give us 4h less than 55. And then divide by 4. We'd end up with h less than, let's do this as a decimal, 13.75. Okay, how do we combine those together? Well, think about our number line. We are saying that we need to be bigger than 9 or equal to from our first one, and we're saying we need to be less than 13.75. Now what's covered by both of those is the space in between 9 and 13.75, so it's just that part there that we're actually interested in. How would you write this down? Our final answer would be that our range is 9 less than or equal to h less than 13.75. We could have a follow-up question here. What's the possible integer values that h could be? Well, it's everything between 9 and 13.75 that's whole numbers, including 9. So just 9, 10, 11, 12, and 13. So yeah, solve both the inequalities separately, graph them on the same line, and try and find the bits that are in both of those lines you drew. So that's it for inequalities. A little bit of a whistle-stop tour through it, but hopefully the main points there have been got across.